All right, everyone.
Sorry about that, Professor.
Hi, let's get started. Uh, Today we're gonna have a short lecture. We talk about water and aggregate. Okay, so the two remaining component for concrete. So we know the major component of for concrete is cement, which is number one, plus water. These two will react. We call that hydration. And then we have different type of hydration products. Okay. We also have mineral mixtures, which we discussed before last week. And Tuesday this week, we discussed chemical mixtures. Okay. The two remaining part is water and aggregate, okay, which will be finished today. Water and aggregate take about the majority of the volume. As you can see here, for aggregate, we have coarse aggregate, which means the larger size stone. The size is anywhere larger than 5 millimeter to 1 or 2 inch. And also we have fine aggregate, which is sand. Okay, anything less than 4.75 millimeter, policy number 4C is classified as sand. Okay, so aggregate, including coarse and fine aggregate, take about 70% plus minus of the total volume of concrete. Okay, water, 15-20%, depending on the water to cement ratio. Okay. For admixtures, not so much. Superplus agent, air entraining agent, uh, very small percentage by volume of cement, by mass of cement. Silica film flash, they replace a certain percentage of cement, maybe 10%, 20 or so. Let's look at water first. Okay.
Water from any source of domestic supply may be used as mixing water for making concrete. In general, almost any natural water that is drinkable and has no pronounced odor or taste can be used. However, there are waters that may not be fit for drinking that can still be used as mixing water for making concrete. Water of questionable quality can be used if 2-inch mortar cubes made with it have 7-day strengths equal to at least 90% of the strength of companion specimens made with drinkable or distilled water. In addition, time of set tests should be made to ensure that impurities in the mixing water do not adversely shorten or extend the setting time of the cement.
So basically, if the water is potable, if it's drinkable, we can use it to make concrete. Okay. Even the water is not drinkable, like seawater, it may still be able to use in concrete, but we need to do some extra test. Okay, let's discuss the video. Okay. Seawater contain a lot of salts, especially chloride. That may be damaging the steel reinforcement. So seawater cannot be used for concrete with steel reinforcement. Okay, too much organic matter, too much salts, they may change in the strength, affect the hydration of concrete, and so on. So we need to limit that. Okay, so like we can see from here, this is the type of impurities. Okay, and the second column is maximum concentration in ppm, and how these impurities can potentially affect the property of concrete. Okay, but basically, if water is drinkable, we can use it to make concrete. If the water is not drinkable, we're gonna do the strength test. Okay, how the compressive strength will be affected. Okay, so limitation is at least 90% of the control strength. Okay, for set time, it should be less than 1 hour earlier or no more than 1.5 hour later compared to the control mix. All right. So yeah, I think that's it about water. Very simple. For aggregate, remember aggregate should be an inert filler, which means typically aggregate should not participate with the hydration process. Okay, no chemical reaction between water, cement, and aggregate. Okay, so the aggregate should increase the so-called dimensional stability. For concrete, one of the major problems for concrete is shrinkage cracking. Okay, concrete will shrink. We call that drain shrinkage. There are some other type of shrinkage, for example, chemical shrinkage, carbonation, or autogeneous shrinkage. But when concrete shrink, it may crack. And when concrete crack, that will reduce the strength and also reduce the durability. Okay. Because aggregate does not shrink, so by adding more aggregate in the concrete, it will increase the so-called dimensional stability. So shrinkage will be less. The stiffness will also be higher because aggregate has higher modulus of elasticity. Toughness will also be higher because the strength of normal aggregate will be higher than traditional cement paste. Aggregate take about 60 to 80% of the total concrete volume. Okay. It will also reduce the cost because aggregate is much cheaper compared to cement, only about 5 to 10% of the cost of cement. Okay. Aggregate will strongly affect the fresh property of concrete, such as the slump, and also the hardened property of concrete, such as shrinkage, creep, and even strength. This table from our textbook showing the property of concrete and how they can be affected by the property of aggregate. Okay, for example, the concrete durability, including the resistance to freezing and thawing, may be affected by the soundness, the porosity, the structure of the pores, permeability of the aggregate, okay, and so on. The resistance to heating and cooling will be affected by the coefficient of thermal expansion of aggregate. Alkali-silica reaction. So that's the potential harmful chemical reaction between the aggregate and cement paste. Okay, so inside the cement we have a lot of alkali. That alkali may react with silica in certain type of aggregate and make the aggregate expand and cracking. Okay, we call that alkali-silica reaction. So presence of certain type of siliceous materials in aggregate will affect how the aggregate will contribute to ASR or alkali-silica reaction. The strength of concrete will be affected by the strength, the surface texture, the cleanness, the shape, the size of aggregate. Okay, and so on. So you can just read from here. Okay, one more. Shrinkage and creep of concrete is affected by the modulus of elasticity, the shape, gradation, and other property of aggregate. Okay. We know we have sand and coarse, which is classified based on the size. Okay, the sand is less than 4.75 millimeter. Okay, so why is not 5 millimeter? So 4.75 millimeter is the clear opening of number 4 sieve. Okay, So number 4 sieve means for every 1 inch of length, we have 4 openings. So we call that number 4 sieve. And that clearance, the size of the opening is 4.75 millimeter. Okay, so the particles passing through the number 4 sieve is called sand or fine aggregate. More than that is called coarse aggregate. The typical size of coarse is less than 2 inch or 50 millimeter. Based on the density, we have heavyweight, larger than 130 pounds per cubic foot. Okay. For normal weight aggregate, it is around 95 to 105. Okay. For lightweight, it's around 75 or less. And depending on the source, we could have natural mineral aggregate, like Moy dune sand or basalt sand, or basalt coarse we use in the lab, belong to natural mineral aggregate. Okay. We could also use synthetic aggregate, such as foam slag and some other type of lightweight aggregate. So we can use synthetic aggregate. We could also use waste and recycled aggregate, such as recycled container glass, okay, or demolished brick, or demolished concrete. Use this waste material to replace natural mineral aggregate. Alright, so let's look at another video talking about gradation of aggregate. So gradation means the particle size distribution of sand and coarse. Okay, and gradation play a very important role on many properties of concrete.
When selecting fine aggregate for the production of concrete, ASTM C33 also requires that the fineness modulus must not be less than 2.3 nor more than 3.1. To determine fineness modulus of an aggregate, add the cumulative percentages by weight retained on each of a specified series of sieves and divide by 100. For example, an aggregate with a cumulative percent by weight retained on each sieve of 2.8% for the number 4 sieve, 9.6% for the number 8, 31.9% for the number 16, 56.5% for the number 30, 79.7% for the number 50, and 93.9% for the number 100, has a total cumulative percent by weight retained of 274.4. Dividing by 100, the fineness modulus of this aggregate is 2.74. Fineness modulus is not a measure of the quality of an aggregate. It is an index number that is roughly proportional to the average size of the particles in a given aggregate. The lower the fineness modulus, the finer the aggregate.
Alright, so for sand, we can calculate the so-called fineness modulus. Okay, here shows the steps. Depending on the sieve size. Okay, so number 4 is 4.75 millimeter, the clear opening. Number 8 is the half the size. Number 16, another half. So number 30, 50, and number 100. So for sand, we do the sieve analysis. I guess everybody, if your undergraduate studies from civil engineering, you know how to do the sieve analysis for sand. But here I just repeat it quickly. First of all, you get a certain amount of sand, and you get all these different type of sieves. The very top is number 4. The second on the bottom is number 8. Then number 16, number 30, number 50, and number 100. Okay, and below number 100, you use the pen. Use the pen to collect any particles smaller than number 100 sieve. Okay, so you put your aggregate on top of number 4 sieve, and you put everything, including the aggregate and the sieves, in a shaker. You shake it for 3 minutes. Okay, and then on top of every sieves, you weigh how much aggregate retain on each sips. Okay, like we can see from the third column. Okay, and they added together should be close to the original total amount of the sand, which we normally use 500 gram. Okay, and from there we can calculate the percentage retained. So for example, 2% retained on number 4 sip, which is equal to 9 over 500, so roughly around 2%. Okay, and for number 8 sip, this is 9 over 500, 46 over 500, so around 9%. And for cumulative percentage, it is calculated based on the percentage retained for all the save size above. For example, number 30 for number 16 save. So number 30 will equal to 19, which is percent retained on number 16, plus 9 retained on number 8, plus 2 retained on number 2. So 19 plus 9 plus 2 is equal to 30. Okay, so on, you can do the cumulative percentage on all the 6 sips. Okay, and then you added all these percent cumulative together. So in this example, it's equal to 283. And the finance modulus is equal to that number divided by 100. Okay, for typical aggregate, that value is around, I will see 2.5 to 3.5. Okay, the smaller number, the smaller the size of aggregate. For example, our molybdenum sand in our lab, that value is around 1.3, 1.6. But for the basalt sand, which is much closer, finance modulus is around 4 or even 4.5. Okay. All right. So any questions about the calculation for finance modulus? Okay. Yeah, it's pretty straightforward, and we discussed this in CEE688, which is the undergraduate class on construction materials. Okay. All right. So let's continue. All right. So gradation curve means when we get the particle size distribution, we can plot a curve which is a function of percentage passing versus the save opening. Okay, we call that gradation curve, a grading curve. Okay. So we could have well graded, which means we have optimal amount of smaller, medium, and larger size. Okay, and for ESTM standard, give a upper bound and a lower bound. The ideal aggregate curve should be fall between the upper and lower bounds. Like you can see from here, the blue line fell within the upper bound line and the lower bound line. Okay, so well-graded aggregate has better workability, less segregation, and better finish. Okay. If the aggregate does not have medium size, we call that gap graded. Okay. So gap graded, it could have segregation problems. It may also affect workability, make the concrete stiffer, which is hard to mix, hard to finish. If the aggregate has no fines, okay, it will reduce the density of aggregate. The concrete may need more cement paste to fill all the voids between the aggregate. As a result, the strength may also be lower. The permeability of concrete may also be higher. Okay, so the ideal situation is we have a well-graded curve for gradation. So for ASTM standard C33, which is standard specification for concrete aggregate, it give upper bound and lower bound, like in this table and in that curve. Okay. So this is for sand. And same thing for coarse aggregate. Okay. Depending on the maximum size. For coarse aggregate, we could have different maximum size. For example, the maximum size could be 2 inch, or 1/2 inch, 1 inch, 3/4 inch, 1/2 inch, and 3/8 inch. Okay, depending on the maximum size, and you choose different upper and lower bound, like we can see from here in the table. Okay. All right. So the gradation is important, as we just discussed. Another new idea or new definition is called packing density or aggregate packing. Okay. So what is aggregate packing density? Let's look at these 3 virtual experiments. So the first one, we have larger aggregate, but the size of the larger aggregate is pretty much the same. And we found out we need this amount of water to fill the cup. So the amount of water will be equal to the total volume of the interparticle space, right? Okay. Then let's look at the second experiment. So the second experiment, we have smaller aggregate, but the size is also pretty much the same. And we found out we need this amount of water to fill the cup. So it turned out the first and the second experiment, we need a similar amount of water to fill the 2 cups. So that means the interparticle space between the first and the second aggregate is almost the same. Or we can call that the packing density for the first and the second is almost the same. Okay. Let's look at the last experiment. For the last one, we can see we have some of the larger aggregate, and also we have some of the smaller aggregate. Okay. So by combining the larger and the smaller size, the smaller particle can fill the gaps between the larger particles. As a result, the interparticle space, which is quantified by amount of water here, is smaller. So we call the third case has a higher packing density. So the void content will decrease when different sizes are combined. In other words, the packing density increase when different sizes are combined. Okay, so like we can see from here, the blue curve is granite. By changing the percentage of the sand, we can find at certain percentage of the sand, the percentage of wood is the lowest. In other words, the packing density at that percentage will be the highest. Okay, the higher packing density actually is better for us because we need less cement paste to fill the gaps between the aggregate. Okay, so for the same amount of aggregate, higher packing density, we can make the concrete more workable. So here shows the correlation between the volume of the cement paste and the dispersion of aggregate. Okay. The amount of cement paste required for concrete is more than the volume of voids between the aggregate. Again, the volume of voids is quantified here as how much water is needed for that cup. Okay. But we need more cement paste just to fill the gaps between the aggregate. Why that's the reason? Okay. The reason is because we need a less stiff concrete. So we need concrete has certain amount of slump. If the paste is not enough, which means aggregate will closely compacted. The particle will interact with each other. If that's the case, the slump will be very low, or even zero slump. Okay. The more cement paste we input in the system, we have more space between the coarse aggregate. As a result, the slump will be higher, the concrete will be easier to work, to mix. Okay. So paste content will affect workability, such as slump, cohesiveness, which is how easy the concrete will segregate, cost, because more cement paste means more cost, shrinkage. The more cement paste means more shrinkage. So the less paste, the better. Okay, and also the permeability. All right. So how much paste is actually needed? To answer that questions, we need to understand what is the function of the cement paste, so we know how much is needed. Okay. So look at this slice. Let's see, initially we have a packed aggregate, right? And we slowly introduce cement paste to make concrete, right? So in the process, we try to mix the system. Okay. So the first part, the first function of the paste is just to cover the surface of the aggregate, like we can see in the red color. Okay. So we need some paste just to cover the surface of aggregate. But still we have a lot of space between aggregate. Okay, so that's the second function or second purpose. When we introduce more cement paste, then it will fill the gaps between the aggregate, as we can see in the blue areas. So the second component or the second function of the paste is to fill the interparticle space. Right. So go back to component 1. So how much cement paste is needed to cover the aggregate surface is affected by factors such as the surface texture of aggregate, the surface porosity of aggregate, and the total surface area of aggregate, which is controlled by size of the particle. Basically, the smaller the particle size, the higher the surface area, and then we need more cement paste to cover the surface of the aggregate. For the second component, the blue area, it is affected by the packing density. The higher the packing density, we have less interparticle gaps, so we need less cement paste to fill the gaps. But we know this is not enough. We need to introduce more cement paste to increase the space between aggregate. So when we mix the concrete, there will be less friction between the aggregate. Right? So we need to increase the paste volume, which is highlighted in this green area. Okay. So increase the particle space to achieve a certain slump, certain workability. So that part is decided by how much slump you need for your concrete. Okay, so that's the three component or three function of cement paste as what is the requirement for that paste. All right. Questions about this? Okay, or comments? All right, let's continue. All right. Apparent specific gravity of aggregate. Okay, so that is a function of the total weight of aggregate over the volume of aggregate. Okay, and the volume of algae including the volume of the solid, and also some internal voids inside algae, like showing this light blue color. Okay, so that internal void means the void is not open to outside, not open to cement paste. Okay. And that ratio is called apparent specific gravity. Divided by raw water. Raw water is the density of water, which is 62.4 pound per cubic foot. Okay. Typical value for ASG of Aggregate is around 2.4 to 2.9. For bulk density, is defined as the total weight of Aggregate in a unit volume. Okay, so we can measure the so-called bulk density and see how much aggregate we can put in a certain volume of a container. All right. So that unit volume including all the volume of aggregate, which is the black area, the internal voids, which is these light blue dots, and also the interparticle space here. Okay. A typical value for unit volume is around 100 pound per cubic foot, plus minus. So here shows the sample calculation. So let's say we have a specific gravity of algae, 2.6. 2.6 means the density of the algae is 2.6 the time the density of water, because this is based on the definition. Okay, divided by the density of water. The bulk density given 120 pounds per cubic foot, which means for 1 cubic foot of volume, we can put 120 pounds of aggregate. Right? And based on that, we can calculate the volume of the solid, which is 120 divided by 2.6 times 62.4. 62.4 is density of water. So the bottom part here is the density of aggregate. So weight over density. So that's the volume of aggregate for 1 cubic foot of unit volume. Okay, so the volume of voids is 1 minus 0.75, so we have 0.26 cubic foot of air per unit volume. Alright, so that's the density and the bulk volume for aggregate. Next, let's look at the moisture condition. Okay, so moisture condition is very important when we design a concrete, because very often on the surface of aggregate we have more or less water, and that water will change the actual water to cement ratio of concrete, because water to cement ratio is the number one factor, the most important factor when we design a concrete. So we better control the water cement ratio closely. So we have to know the moisture condition for the sand and the coarse aggregate, so we can control the water to cement ratio. Okay, so that's why we care about the moisture condition for aggregate.
The amount of water an aggregate will absorb depends on its porosity. The more porous the aggregate, the more water it will absorb. There are 4 designated moisture conditions for aggregates. They are oven-dry aggregate, containing no moisture at all; air-dry aggregate, containing less moisture than it is capable of absorbing; saturated surface-dry aggregate, when all permeable voids in the aggregate are filled and there is no water on the exposed surface; and damp or wet aggregate, which is aggregate containing free moisture on the surface in addition to having all the voids in the aggregate filled with water.
Alright, so we have 4 moisture conditions for aggregate. Okay, from dry to wet, we have oven dry, which is no water inside and outside the aggregate. So we put the aggregate in the oven dry for a day, so we get oven dry condition. All right. The second one is called air dry. For air dry condition, on the surface there's no water, but inside the pores is called permeable pores, which means the pores opens to the air. Okay, so the permeable pores are partially filled. Right. The third one is a very special moisture condition. It's called saturated surface dry. The surface is still dry, but the permeable pores are fully saturated. As we can see from here, all the permeable pores are filled with water, the blue color. Okay. We call that special situation, saturated surface dry, or SSD condition, because only under saturated surface dry condition, the aggregate will neither absorb water or give water to the cement paste. Okay, because if the aggregate give water to the cement paste, then the water cement ratio will be higher than we needed. If the aggregate will absorb water from the cement paste, then the water to cement ratio will be lower than we designed. Right? Okay. Look at the last one. Wet condition. The inside the pores are saturated, and outside the surface we have a film of water. Okay, we call that wet condition. All right. Also, we have some new definition, such as absorption capacity. This one is very, very important. Okay, so that's the difference between WSSD, which is the weight of the sample in saturated surface dry condition, minus WOD is the weight of the sample in oven dry condition, over WOD. Okay, so absorption capacity basically means how much water or oven dry aggregate can absorb to become saturated surface dry condition. Okay, so that property is an intrinsic property for certain type of aggregate. That means for certain type of aggregate, absorption capacity does not change at all. Okay. And we also have, less important definition, surface moisture, which is difference between wet condition and SSD condition, and effective absorption, which is difference between SSD and air dry condition. But the most important one is this, absorption capacity. Okay, again, the most important thing is, remember, when mixed in saturated surface dry condition, the aggregate will neither absorb nor give up water to cement paste. And we should always use saturated surface dry condition when we design our concrete. Alright, so we will learn how to design a concrete mix next week. Okay. So let's see, from mix design, we get the saturated surface dry weight of aggregate, because again, always use SSD weight in our mix design. So let's say after design we get saturated surface dry weight of aggregate. But how to adjust the mixed water and the stockpile aggregate based on daily condition? Okay. Then we need to know the so-called moisture content of the stockpile aggregate. Okay. The moisture content, or MC, is defined as the weight of stockpile aggregate minus the weight of saturated surface dry aggregate over weight of saturated surface dry aggregate. Okay, so we need the moisture content, which is a percentage. moisture content could be positive or negative. Positive means the moisture content for the aggregate is wet, and the water need to be subtracted from the mixing water. If the moisture content is negative, then the moisture content will be air dry, then water is added to the mixing water. Okay, we're going to talk about how to deal with this in the future. But let's go back a little bit. So we know we need moisture content, right? Okay. And we need W stockpile to do the calculation. Okay. So W stockpile is easy to do. We just get a certain amount of sample, we wait, we know W stockpile. But WSSD is kind of hard to measure because it's the weight of aggregate in saturated surface dry condition. Okay, and saturated surface dry means surface no water, but inside is fully saturated. It's kind of difficult to achieve that moisture condition for aggregate. If you take CEE688 before, in the lab, we know how to get the acid condition for sand, which we use a hair dryer to dry the sand, and we need to use the corn to measure the moisture content for the sand. And for coarse aggregate, we need a towel to dry the surface of aggregate for every single particle. So very time consuming. So measure WSSD is not very realistic in real situation, but we can use the second equation to calculate WSSD based on AC. AC is the absorption capacity. As I just mentioned, absorption capacity is intrinsic property of aggregate, does not change for that type of aggregate. So AC is known, we know that already. And we can also easily measure WOD, so which means weight of aggregate in oven dry condition. WOD is very easy to measure. So we put aggregate from the stockpile, we put that in oven overnight, then we measure W oven dry condition. So instead of measure WSSD, we can use the second equation to calculate that, and then we plug in the number WSSD, so we get moisture content. All right, and then we can do the adjustment to the mixing water, which will be done when we discuss mix design. Okay, but today we should know the full moisture condition and how we can calculate the moisture content based on this value. Okay. All right. So any questions so far? Okay, let's continue. The size and the shape will also affect the property of concrete. The more sand, we need more water to mix the concrete because the smaller particle has a higher surface area. We need more water to compensate that. Okay. Coarser aggregate is cheaper to manufacturing because we need the grinder to crash aggregate into smaller size. Okay, so larger particle size is cheaper to do. Okay, and the higher the size of aggregate, we need a lower amount of cement paste, and the strength will also be lower because we have higher internal stress concentration. So what does that mean? That means, remember, for concrete we have cement paste and aggregate. And cement paste and aggregate has different modulus of elasticity. Okay. When we compress the concrete, the paste and aggregate will have different response because they have different modulus of elasticity. Okay, so the higher the size of aggregate, the stress around the boundary between the paste and aggregate will be higher. We call that higher internal stress. Okay, so again, this internal stress is caused by difference in modulus of elasticity between cement paste and aggregate. Okay, we're going to talk about this more in future lectures. And also for the size of aggregate, we have some guidelines. Typically, the size is less than 1.5 inch. Okay. For high performance concrete, it prefers smaller aggregate because smaller size aggregate, we're gonna have higher strength. We have also requirement for the maximum size of aggregate as a ratio of minimum for size of form. Okay, so less than 20% of the minimum dimension of the form, and also requirement between the size of aggregate and the clear spacing between the reinforcement. So that is to make sure when you pour the concrete, there are no blockage between the spacing of the reinforcement. Okay. And here shows the aggregate proportioning based on the size and the air content. Okay. And here is how the maximum size of aggregate affect the total volume of the water, cement, and aggregate. Okay. So basically, if we increase the size of aggregate, we need less amount of water. Okay. And we can also increase the amount of aggregate. And here is how the size of aggregate affect the water content. So increase the size of aggregate, we need less amount of water to make the concrete workable. Okay. The shape of and the texture of the surface for the aggregate will also affect the performance of concrete. Angular shape, rough surface, or elongated shape, that will increase requirement for cement paste. We also reduce the slump. Right, so here is a summary about how the shape of aggregate affect the performance of the concrete and also the surface texture. Okay. Right. If the aggregate has some impurities, such as on the surface of aggregate we have clay, and in the clay we have some organic matter, that may affect the strength and also setting time even. Okay, so we should pay more attention about organic impurities. And even the particle size, if the material is too fine, finer than 75 micrometer or number 200 safe, that will reduce the bond between cement paste and aggregate, and also reduce the strength of concrete, and also increase how much water is needed. Okay. Some other potential harmful materials, okay, they may affect the durability, volume stability of the aggregate, may cause pop-up of the aggregate from the concrete. Okay. And ASR. Okay, ASR is the reaction between cement paste. So cement paste will provide alkali. If the silica in the aggregate is reactive, then we could have alkali-silica reaction. Okay, so this is reactive silica from the aggregate plus sodium hydroxide, which is NH. KH is potassium hydroxide. So that's coming from the pore solution. Together with water, we have expansive alkaline silica gel. So that gel is whitish. The color is white. If the concrete crack from inside of the expansive aggregate, we may see whitish gel coming from the cracks from the inside the concrete. Okay. So in this short lecture, we discuss water and aggregate. Okay. For water, it's pretty straightforward. When the water is drinkable, we can use it to make concrete. If the water is not drinkable, we're gonna do some tests to verify that. Okay. We also know how to calculate the finest modulus of the sand. What is the flow moisture condition of aggregate? We have air dry. First of all, oven dry, air dry, saturated surface dry, or SSD, and wet condition. Okay, and we need moisture content of the aggregate before we can do the adjusting for the mixing water when we do the concrete mix design. Okay. All right. I think that's it for today.